The purpose of this video is just to give you a little calculus primer so that later on, if we haven't covered these topics in detail in calculus, you can at least go through the motions, and then once we get to the calculus later, you'll understand the details of the theory behind it instead of just the mechanics. So it's kind of the mechanics. And by the time you watch this, you probably will have had some of this already. So basically three things that we do in calculus. We deal with the concept of limits, which we probably already talked about in calculus, and then we talk about derivatives. And derivatives are basically just the slope of the tangent line to a curve. So let's say we have a graph, and here's the curve. And if we draw a tangent lines are where a line would just touch the curve at that point. So you're used to that with circles. You talk about tangent lines for circles. So here's a circle, and you have a tangent line. So this would be a tangent line to the circle at that point, and that would be a tangent line at that point. For circles, the tangent lines are always perpendicular to the radius to that point. So these are always 90 degrees. So for functions, it's a similar kind of thing. That line would be tangent to the function at this point, and this line would be tangent to the curve at that point. And those tangent lines have slopes, and the slopes of those lines are derivatives. So what we do in calculus is we give you techniques to calculate what the value of the slope of the tangent line is at particular points. So as it relates to physics, in the first semester, we deal a lot with displacement, velocity, and acceleration, which are functions of time instead of functions of x. They're functions of time. And they're related to each other. The velocity is equal to the derivative of the displacement with respect to time. We use this ddt designation. So this ddt of x means the derivative of the displacement as a function of time, and that is the slope of the tangent line at any point in time. So if I draw displacement or plot displacement versus time for some kind of object, and it looks like this, and I want to know what the velocity of the object is at a particular point in time, I can find that by just finding out what the slope of the tangent line is at that point, and that slope is the derivative. And then finally, the acceleration is the derivative of the velocity with respect to time. So how do you find, if you're given x as a function of time, how do you find v of t? And if you know v of t, how do you find a of t? Now, in physics, most of the descriptions of the displacement as a function of time are polynomials. Now, in calculus, we'll get into all other kinds of functions, trigonometric functions, logarithms, exponentials, inverse trig functions. But for physics, they basically want to show you how to do it, and it's the easiest thing to take derivatives of is polynomials. So if you said the displacement as a function of time was equal to 5t squared plus 5t plus 7, so that would be a parabola. Then you could plug in a value of t and get the displacement as a function of time. It looks something like this, except at t equals 0, you'd already be displaced 7 units. So to find the velocity is a function of time, you take, we would say, the derivative with respect to time of the displacement. And for polynomials, it's a simple equation formula, and I'll tell you what that is in just a second. So let's say you have x is a function of time, and it's some constant. We'll call it x0. Actually, that's not what I want to do. Let's say it's let's just say it's c, some constant c, times x to the n power. And n can be an integer, or it can be it just has to be typically it's going to be a positive integer, but it doesn't have to be an integer. It could be a rational or irrational number. So it can take on any value. So that's if the function is a polynomial. So in this case, c would be 5, n would be 2. For this part, c would be 5 and n would be 1. And for here, c would be 7 and n would be 0. What we'll find out in calculus is that the derivative, and actually I should be using t here instead of, so sorry about that. That's the thing about physics, we use t. So it's a function of t in this case. So if you take the derivative with respect to time of this x of t polynomial, or the derivative with respect to time of a polynomial with a constant times t to some n power, to do the derivative, what you do is the constant just stays the same, and then you take the exponent, which is n, and you multiply that by t to the n minus 1 power. So let's look at each one of these. Let's say x of t is 5t squared. The velocity is going to be the derivative with respect to time of 5t squared. So it says it's going to be, c is 5, so you get 5. N is 2, that's the exponent, so you get 2. And then t to the 2, n is 2 minus 1. So you can simplify that. 5 times 2 is 10. 2 minus 1 is 1. But t to the 1 power is just t. So if the velocity is a function of time is 5t squared, then the displacement is 5t squared, then the velocity is 10t, where t is the time. Okay, so let's do another one here. Let's say x of t is 5t. Then the velocity as a function of time is going to be the derivative with respect to time of 5t, which is the derivative with respect to time of 5t to the 1 power, just so I fit it into the form. So if you take the derivative, you're going to have c, which in this case, c is 5, times the exponent, which is 1, raised, multiplied by t to the n minus 1. So you get 1 minus 1. So you get 5 times 1 times t to the 0. Any number or variable raised to the 0 power is just 1. So you get 5 times 1 times 1, or 5. So if the displacement as a function of time is 5t, then the velocity is 5. So if the displacement is linear, the velocity is constant in this case. And then the final one is if you just have a constant, which I think I had 7. Well, it turns out, so the velocity, if you're at a constant displacement, then you're not moving. So if you take the derivative with respect to time of a constant, it's 0. So constant displacement is 0 velocity. So anytime you have just a constant without t, this has t and t squared. So the derivative of a constant is 0. So if you go back to this multiple one that involves all 3 kinds of terms, then if x of t is a polynomial, which is a sum of 3 terms, you just do them individually. So we did them individually. So the derivative of 5t squared was 10t. The derivative of 5t was 5. The derivative of 7 is 0. And that's velocity as a function of time, not displacement as a function of time. So the velocity is 10t plus 5. So that's how differentiation works with polynomials. It's pretty straightforward. Now if you wanted to find the acceleration as a function of time, then you would take the derivative with respect to time of the velocity. So again, we have a polynomial here. It's a simpler one than we started with. So again, you take the derivative of each one of these separately. So if you remember, the derivative of 5t was 5, so the derivative of 10t is 10. And the derivative of a constant is 0. So the acceleration as a function of time is 10. So you always, when you take the derivative, your polynomial gets simpler. Here we have t squared, here we have t, here we have just a constant. So that's the basic idea of when you're using, you're finding derivatives of polynomials, you use this formula. They're pretty straightforward. They'll usually give you t squared, t, or some constant. They won't. I don't think they'll give you a non-integer, but if it was a non-integer, you'd still use the same formula. If this is 2.1, then the derivative would be c times 2.1, t to the 1.1. We just subtract 1. Okay, so that's derivatives. That's typically when you're given displacement as a function of time, you want to find the velocity as a function of time and then find the acceleration. And, displacement is going to be in meters. Because you're taking the derivative with respect to time, your velocity is in meters per second. And the derivative, again, with respect to time, you end up with the acceleration in meters per second squared. I didn't show the units here. I'm just showing you them as polynomials. Okay, so that's pretty straightforward. The other way is sometimes you're given acceleration as a function of time. Let's say it's 10 meters per second squared. And the question is, what is the velocity as a function of time and what is the displacement as a function of time? So let's go in the other direction. So here I was given displacement as a function of time. Somewhere back here. I was given displacement as a function of time. I wanted to find velocity and acceleration. Sometimes you're given acceleration and you want to go the other direction. It's not quite as simple. It's fairly simple, but one other thing you need to know is to be able to do this, you have to know the what we would say is the initial velocity is some value. Let's say it's 5 meters per second, and you need to know the initial displacement. That means the displacement at time t equals 0. So you have to have a as a function of time as a polynomial, which is this is constant, is the simplest polynomial, and then you have to specify the initial velocity and the initial displacement. Okay, so what we're doing here is there's two ways you can think about it. One is you can think about an integral. What we're talking about here is integrals. And there's no R there. Integral, not integral. Okay, so there's two ways of thinking about integrals. Are the opposite of derivatives. And there's two ways of thinking about it. One is that you know basically know the slope of the line as a function of time, and you want to go the other direction. So let me go back to my picture here. So here we have the line, and we want to find out what the slope was. That's the derivative. If we know the slope, can we figure out what the line is? The answer is yes. We'll talk about that in Chapter 6 in physics and the calculus. It's called solving differential equations. So it's kind of like, I know the derivative with respect to time of the thing I'm trying to figure out. And I also know the initial value of x. I want to then be able to calculate x as a function of time. So in this case, if I'm given the acceleration as a function of time, I want to be able to calculate the velocity, which is the velocity is a derivative. The acceleration is a derivative of the velocity, so it's going the other direction. So that's kind of like solving differential equations. The other one is doing it more from a graphical standpoint. So let's say I have a plot of the acceleration as a function of time. So here I have an equation. If I'm thinking about, here's acceleration as a function of time, what is b as a function of time? Question mark. So the way you can look at it there is you can say the velocity is equal to, we use a symbol, this integral symbol. The velocity is equal to the integral of the acceleration from t equals 0 to t equals some value. We'll call t star. So let's call this t star right here. That's some value t. Well, the integral is the area underneath this curve. So it says the velocity at a particular time is the area underneath this acceleration as a function of time. And then you have to apply this, you have to use this initial condition stuff. Okay. For right now, we're going to look at it from this perspective. We'll talk about this a little bit in class, but I'm just going to show you the mechanics of how it's done. So to find the integral, so let's say, so what we're doing is we said velocity as a function of time is the integral of the area from t equals 0 to some value t equals t star. Okay. To do this integral thing, so the integral of some a of t dt, where a of t is some polynomial x to the n power, and this has to be t to the n power, okay. T to the n power dt. So your acceleration is some polynomial. So let's just we'll make it something not too complicated. So it's a linear, the acceleration is a linear function. The integral is equal to t to the n plus 1 over n plus 1 plus some constant. The constant, we're going to use the initial. Let's see, we don't want to do that. We're just going to say it's that. For right now, you'll understand more details when we get to the calculus, but for right now, to get the integral of a polynomial, you take the old polynomial, you add 1 to the exponent, you divide by the new exponent. If there's a constant, let's put a constant here, just so the constant just is multiplied by the whole thing. So, if I said, what's the integral of 2t dt? 2 comes out, the exponent is 1 in this case. We don't show the 1 when it's just to the first power. So you take 1, the old exponent, you add 1 to the old exponent, so you get t to the 1 plus 1 power divided by 1 plus 1. So in this case, n is 1. So the integral is 2 times t to the second power divided by 2, which equals just t squared when you simplify it. The integral of a constant, so let's say 5 dt how do we fit 5 into this form? Well, it's 5 times t to the 0 power dt. So when you have t by itself, it's t to the first power. When you have no t, it's t to the 0 power. T to the 0 power is 1. So this simplifies down to that. So again, the constant just hangs on. You've got the variable. You add 1 to the old exponent and divide by the new exponent, which is 0 plus 1. And so what you get is 5t divided by 1, which is 5t. So the integral of 2t dt is t squared. The integral of 5 dt is 5t. Now you end up with, when you do this integration, so the integral of 2t plus 5 whole thing times dt is t squared plus 5t plus some constant. So anytime you do an integration of a polynomial, you get this more complicated polynomial plus this constant. And this constant is determined by using the initial values for the function. So let me demonstrate. So again, let's say the acceleration is 5t plus 5. Therefore, the velocity as a function of time is t squared plus 5t plus this c. But what I would do is you'd have to specify, you'd say the velocity at t equals 0 equals 3 meters per second. So this is what's called an initial condition. So this tells me what the velocity is at t equals 0. So the way you do this is you say, okay, let t equals 0 and v of t equal v of 0, which is 3 meters per second. So I use that initial condition to figure out what this constant is. So v of t is v of 0, which is 3 meters per second. That's equal to 5 times 0 squared plus 5 times 0 plus c. So c equals 3 meters per second. Because 0 squared is 0, 0 times 5 is 0. These two initial terms go to 0. So using the fact that my acceleration is this polynomial and the initial velocity is 3 meters per second, then I can say that v as a function of time is equal to t squared plus 5t plus 3 meters per second. So you can see if I take the derivative of this, I'll get that. And it doesn't really matter what this number is. The velocity as a function of time, the acceleration is going to be the same no matter what this arbitrary constant is. This constant, the constant is set by this number. So if v of t equals 0 is 5, then it would be t squared plus 5t plus 5. And the derivative would always be equal to this thing. So it works in the opposite direction. Now, also the displacement is the integral of the velocity as a function of time. So what we do mechanically wise is we would say that and let's say x at t equals 0, the initial displacement is 10 meters. So the process of going the other direction, you take the integral of the velocity I got from the previous step. So it's t squared plus 5t plus 3, whole thing times dt. This dt tells us which variable we're integrating with respect to, which in this case is the time. So we use the formula. So we do each part separately. So the integral of t squared is we add 1 to the exponent. So this becomes 3 instead of 2, and we divide by the new exponent. Okay, if we have a constant, we just put it out front. And I realized that I forgot, I messed up here. 5t over 2. Okay, I don't know why I did that, because I was just thinking about the integral of, maybe it's because I had 2t, oh yeah, because this was 2t, that was why I got confused. Oh, okay, so my problem here is I should have made this 2, so let's just fix that. Then it makes sense, so it's just this initial thing should have been 2. So that works out. That works out. No 2. Okay, sorry about that. Okay. I think all that's right now. Okay. So let's, yeah, everything's good. Okay. So here we have 5, so we add 1 to the exponent. So the exponent is 1, so we add 1 to that. It gives us 2 divided by the new exponent. And the integral of 3 dt is 3t to the 0, so you add 1 to the exponent, you get 3t to the first power, and then you have this constant again that you add to the whole thing. And so to find the constant, you'd have to apply this initial condition. So we say x of 0, t equals 0, is equal to 10 meters. That's equal to 0 seconds cubed over 3 plus 5 times 0 seconds squared over 2 plus 3 times 0 seconds plus c. And you see all this stuff goes to 0. So you get c equals 10 meters. And so our final answer, the displacement as a function of time, is t cubed over 3 plus 5t squared over 2 plus 3t plus 10. And so, again, let me just review what I just did. If you're given your acceleration as a function of time and your initial velocity, you can apply the formula for integration of a polynomial to each term. So the integral of 2t is 2t squared over 2, which simplifies to t squared. The integral of 5 is 5t. You add this constant, then you use the initial condition to find out what c is. And with polynomials, c is pretty much the initial condition. But this is going through it formally. You put in t equals 0, and those terms drop out, the ones that involve t, so you find c is 3 meters per second. So if you put t equals 0 into here, you get 3 meters per second, which matches up with the initial condition. Then you can do the same thing for the displacement. You take the integral of v as a function of time. So we take v as a function of time, where I've applied the initial condition. And you apply the formula, this formula right here somewhere. This one. You apply that. So here's the velocity as a function of time. Then to integrate it, you add 1 to the exponent, divide by the new exponent. The constant stays the same. You add 1 to the exponent, divide by the new exponent. Here we have t to the 0 power. So you add 1 to 0, and you get 1 divided by 1, so you get 3t. You add this constant. Then you apply the initial condition that you're given. So the initial displacement is 10 meters. Plug in t equals 0, so the first 3 terms go to 0. All you're left with is the constant. So the initial condition allows you to figure out what this constant is. You plug that back in, and you get the answer. So that's the whole concept of differentiation and integration relating to polynomial descriptions of displacement and acceleration. If you're given the displacement, then you can take the derivatives to find the velocity and the acceleration. if you give the velocity, you can calculate the acceleration by taking the derivative. If you want to go the other direction, you use the integration formula. You not only need to know the acceleration to find velocity, you also need an initial velocity to find out what that constant c is. And likewise, if you know the velocity is a function of time and you know the initial displacement, you can then use the formulas to do the mechanics of finding the integral of those polynomial terms, and that allows you to do it. So that's the whole idea behind calculus, the calculus part of physics when it comes to Newton's second law, or actually not Newton's second law, just the relationship between displacement, velocity, and acceleration.